Welcome back. For the last track of the hardware session, we are going to go and talk some more about some interesting play with both physics and exploits that are going on. A lot of the time when we are getting vulnerability reports, we're all thinking about remote execution. But as you can tell with the last presentation, some of the adversaries and threats that our customers are facing don't necessarily assume that you don't have, the bad guy doesn't have access to your hardware. Ollie and Pasi are here to challenge us a little bit on what we're doing in the operating system and how we can protect customers if the attackers actually get access to their hardware. So with that, please welcome them to the BlueHat stage.
Thank you, Philip. Can you guys hear me okay? Yeah, good. Okay, so I'm Ola, this is Pasi. We're consultants, so by day our job is basically helping our customers get better at doing security, protecting themselves, and sometimes that means actually going and breaking their stuff before somebody else does. So let's see if we can get slide transitions going. Yeah, so this was actually something that started out at a customer assignment. So a customer of ours came to us and said, we have these, we're basically upgrading our whole fleet of client laptops, client machines, I should say, to Windows 10, and we're buying all new hardware, and we think we've done a good job of setting everything up and hardening everything. We think we've done a good job with detection. So could you guys just have a look and see if there's anything we missed? So we put together a proposal for them where part of it was just, okay, let's run through the scenario that somebody has lost their laptop in a taxi or it was stolen in a restaurant, something like that. Just give us a couple of machines and we'll pretend that they're stolen and we'll see what we can do with it. And then, of course, we had several different other options later on where, once we get into a machine, can we get into their network? Can we persist malware on a machine? That kind of thing as well. But this was like step one of this scenario that we played out. So since they'd configured it correctly, like according to all the Microsoft recommended settings, they were using BitLocker, of course. So we kind of figured our first step would be to have a look at how do we actually get to the BitLocker keys to be able to unlock the hard drive, steal secrets, or perhaps even plant a backdoor on there. So there's several different ways that you could get to those keys. So you could, for example, use the key escrow system that's built into BitLocker. So every time you set up BitLocker, it's going to save some recovery keys. Either if you're a consumer, it's going to save them with Microsoft Cloud. If it's a domain joined machine in a corporation, it's going to save them in the Active Directory. But that was kind of out of scope for the testing that we were doing for our customers. So, we weren't about to, call up help desk and ask for the recovery keys. You could kind of talk to the TPM chip that holds the keys when the machine is off and try to fake communications with the TPM to try to fool it to giving you the keys, but that was a bit more work than we were prepared to do initially. So we had to look at, okay, these keys that encrypt the information stored on the hard drive have to be in RAM because the BitLocker is part of the operating system. The operating system is doing the encryption and decryption of the data before it goes to the hard drive. Therefore, the encryption keys have to be in memory somewhere. So how can we get at those keys in memory? Well, our friend Ulf Frisk has this nice PCI leech toolkit that you could use to kind of extract memory from the machine by connecting to, for example, a Thunderbolt port or something like that. But Thunderbolt protections were in place there as well. They followed those recommendations. You could remove the RAM chips from the machine and put them into another device to read out the contents. But, either those RAM chips were soldered to the motherboard, so that wasn't an option, or we figured there's probably easier things to do. So we had two options left on our attack path mapping, which was either we attack the OS directly, so if we have a machine, we can connect to it over the network, something like that. Sooner or later, there's going to be some kind of vulnerability we can use to exploit to get onto the machine, or we can try out these cold boot attacks. And I'm guessing that you already figured out that we chose the second option. So quick recap on what is cold boot attack. Basically, like I said, the RAM contains secrets when the OS is booted up and running. Could be things you're typing into a document, could be passwords, could be these encryption keys, right? And the contents of RAM aren't lost immediately when you power down the machine. So sometime after, let's say a couple of seconds after the RAM chips lose power, it'll start to degrade enough that you won't be able to recover the contents. But if you cool down the RAM chips to a freezing temperature, this remnants effect gets stronger and the contents of RAM will be preserved for a longer amount of time. So that kind of increases your chances of getting at those contents. So you have two possible approaches to getting at the contents of RAM. One would be, like I mentioned earlier, to actually cool down the memory chips, remove them from the machine, put them in another machine, and read out the contents that way. That's finicky, it's fiddly and difficult, and it takes a bit of time. Like I mentioned earlier, if the RAM chips are soldered directly to the motherboard, as is increasingly the case with modern machines, that's not an option you have. So the easy way is just to leave everything in place and boot another operating system off of an external media, for example, to just dump the contents of memory. So that's the route we went. And this is exactly what researchers from Princeton University showed 10 years ago. I think that they might have coined the term cold boot attack. I'm not totally sure about that, but they definitely popularized it. And they published all of their research tools. So you have like proof of concept code to actually do this attack of dumping the memory, booting from like Pixie boot or USB drive, and dumping the memory and then analyzing the memory contents to find those encryption keys. All of that was published already 10 years ago. So basically nothing new. But our good friend and colleague, Timo Hirvonen, presented at a Finnish conference last year about actually updating this and modernizing it, putting it into a form where it's actually practical. Instead of research tools and proof of concept tools, actually making this into a practical attack and updating it for modern firmware, which uses modern platforms which use EFI firmware and not older BIOS stuff. So we thought that, great, he's done all the hard work. It's going to be easy for us. So we'll just, cool down the RAM chips. We'll put Timo's code on a USB stick, boot from that, and we'll be fine, right? But turns out when we did that, dumped all the memory, saved it to the USB stick, analyzed it on a separate machine, and saw that basically all of the contents of memory were wiped. It was all zeros. So we had to kind of figure out, okay, if we're going to do this, we have to figure out why is the memory contents being wiped, and what can we do to kind of bypass that. So what we did was just buy a cheap chip programmer off eBay with a test lead, put it on the SPI flash chip to read out the BIOS, and that's basically what, if you saw the previous presentation, is you'll recognize this tool, UEFI tool, which can then tell you what's on that SPI flash chip. In this case, the machines that we got were kind of new machines, latest platform revision from Intel, using Intel boot guard, which means that the firmware is actually signed. So we couldn't just go in and patch out the code that was doing the memory wiping, because there are integrity protections in place, right? But we did find that there are other regions or other volumes in this SPI flash. For example, this EFI variable store, which is basically, if EFI is your BIOS, then these NVRAM variables, EFI variables, are your BIOS settings, or where they're stored, basically. Stores a lot of other things as well, but that kind of information is stored there. And those aren't integrity protected because they're supposed to be changed, right? You're supposed to be able to change those settings. So scrolling through that list of EFI variables, we found one that had like an interesting ring to it. It was called memory overwrite request control. So we thought, this is probably something we should look into. So Pasi can tell you what happened then.
Yeah, so the first thing you do when you find something interesting, you Google it. And what we found was this lovely specification, the platform reset attack mitigation specification. published the same year as the cold boot attack was published, which is actually very impressive that it was done. So maybe it wasn't a response, or I'm not really sure. But
seems like it.
Basically, the specification describes how they prevent this cold boot, original cold boot attack, by having a bit that is used to flag if the computer has been crashed. So in a normal scenario, the computer starts up and you will load your secrets into memory, and part of the shutdown process when you're finished is cleaning out the secrets from memory. So the realization is that if the computer is crashed, then you never did this cleaning of the memory, so you need to have some other part do that for you.
And that's what this bit is signaling. It's the OS telling the firmware that, secrets are in memory. If you don't hear from me, then please wipe all of memory to be safe, right?
Yeah. So basically the flow here, you can see how
You should probably switch to that
see.
one.
Okay.
Right?
So this is the flow in case you crash the machine. The computer starts up, the BIOS reads the memory more bit, as it's called, and realizes it's 0 in the first case. And then when it's starting, it sets the bit like I have booted, I have secrets in memory. And then when the OS is crashed, in the normal case, if it was shut down, it would have cleared this bit. But when it's crashed, it doesn't clear this. So the next time the computer boots, the BIOS will realize, oh, this bit is still set. I need to clear the memory to make sure that there are no secrets left here. So that's a very easy fix to a complex problem. So reading through the specification, we found these lovely sentences. And if we look at the first sentence, which is informational, you can see that requires the BIOS to attempt to detect any potential tampering with the Morbit. That would be awesome. But this is an informative comment in a specification. So it's actually not required to be implemented. Even though it says required, and the normative text also says that it should detect, but it's not as clear. And so, of course, it doesn't, yeah. Of course, we need to check that it's actually doing that. So, back to the drawing board, we have this lovely tool to dump the memory, so we start working with that, but of course that's not practical to reprogram the whole flash chip every time, so we start working on this very basic Arduino-based programmer that will just program this single bit. And
yeah, so this is just an example that this is not magic. It's not something very complicated. You can just Google for instructions online, like from Trammell Hudson's webpage here that we show you, and basically we just follow those instructions, let's say, or just use a different piece of hardware, but still just a cheap, easy microcontroller off eBay that you can program directly in C to talk to an SPI flash chip. And then we have the flexibility to actually be able to perform this attack instead of using an off-the-shelf chip programmer, which would just support reading and writing the whole chip, right? Yeah.
Yeah, so this is just a picture of
our first prototype.
Yeah. Yeah. And it worked very well. With this chip clip, it's easy to connect to the SPI flash. You don't have to solder anything. So, demo time. How do you start?
Unfortunately, we don't have all of the stuff here to perform a live demo for you guys, but we do have a pre-recorded one. Yeah, so the user is using his laptop. He has some secret password stored on the hard drive. He leaves his laptop unguarded for a moment, and the evil hacker comes and steals it. Plugs it into the AC power, removes the battery and the case to get to the flash chip on the motherboard, cools down the RAM chips, plugs in a USB drive, tampers with the firmware settings, and reboots the machine. Uses Timo's nice tool to dump the contents of memory, find the AES encryption keys, and mounts the hard drive using Linux. And there's your secret passwords. So it can be that easy, basically. And, well, yeah. Before you applaud, there's one caveat. So, yeah, go ahead.
Well, we should mention that there was some cutting in this video, but all in all, the attack takes 2 minutes, something like that.
It depends on how hard it is to unscrew the screws, right? That's
And how much memory you have.
Yeah, it can take like 20 seconds, perhaps, if you've got 16 gigs or more.
Yeah. So, of course, you need to have something in the RAM so that we can steal it. So if you start the machine as an attacker and you see this, then you're screwed. There's nothing in the RAM, we can do nothing. But if you open the case or open the lid and you see this, then you have secrets in memory and we're good to go.
Yeah. So a comment there would be that, for example, if you're running Windows Home licensed, if you're running home licensed Windows, for example, if you bought a retail machine off of Best Buy or whatever, and that home licensed Windows still in Windows 10, I think, does not support actually using BitLocker with a pre-boot authentication PIN, which means that every time you press the power button to start up the machine, it'll boot fine and give you the Windows login prompt. And like Pasi mentioned, that means that during that process, the encryption keys will have been loaded out of the TPM chip into RAM, and they're there for the stealing.
But I guess people were wondering, like, I have all these BIOS protection things, shouldn't they protect from all of these?
Yeah. So, for example, we mentioned TPM. So I've got TPM protection, I've got secure boot enabled, all of that stuff. We mentioned we boot from a USB drive. Perhaps we've locked that down in the firmware settings, so you can't boot from an external device. Setting a BIOS password to disable booting from another device than the hard drive, for example, might help. Or, even the machine that we first started this research on actually had some tamper switches on the motherboard, so that when you open the case, it trips those tamper switches and the machine won't boot anymore. So, all of these things might be stuff that would prevent such an attack, but we thought we'd go through all of those steps and show you how they also can be bypassed. So, secure boot, for example, is designed to prevent people from getting in between the firmware initialization and the OS start and tampering with the code in between there. So it only allows bootloaders, EFI programs signed by Microsoft to run. But to be able to boot Linux, for example, there's a special bootloader that you can use as a shim in the middle between the EFI firmware and your OS loader, which is signed by Microsoft to allow these Linux distributions to actually work on modern machines with secure boot. And the shim bootloader actually allows you to manually enroll a whitelist of EFI programs that are allowed to boot if you have physical access to the machine. It looks like this, for example, where you just choose which file to trust, and then you've bypassed the secure boot protection and can boot anything. We mentioned as well boot order. You might have something locked down in BIOS settings where you're not booting off of external devices, not Pixie booting, not network booting. Those settings are also stored in an EFI variable, probably one called boot order, most commonly. And since that's stored in an EFI variable, when we're tampering with the more bit, which is also stored in an EFI variable, we can just as easily tamper with the boot order to change the boot order to make it boot from USB first. So you could even re-enable disabled boot options using the same method. And failing that, I mean, worst case, we have physical access to the machine. Could probably remove the boot device, the SSD or the hard drive, and just plug in something instead. That would be feasible in this kind of attack scenario. So that won't save you either. And we mentioned BIOS passwords being a good protection to protect these settings from manual tampering using the keyboard. Unfortunately, modifying the firmware can most oftenly either bypass the password protection or just clear or change the password. So there's a nice web page at bios-pw.org, and it looks like this. If you enter your, in this case, serial number or service tag, I think it's called, because this is Dell, it actually gives you a master backdoor password for that machine that'll let you remove the BIOS password. Really quick and easy. So the BIOS password would probably not save you either from this kind of attack where...
Especially if it's a Dell machine.
Yeah. Some vendors are better at protecting the password than others, but most of them do have some way of recovering from a lost BIOS password, because users tend to forget passwords. Tamper detection, you have these nice tamper switches on the motherboard. You might think that would save you from an attacker opening the case to get to the SPI flash. Well, not unless the attacker knows how to use Google. eBay and teardowns on Google image search are really easy to find where these switches are located. And if you know where the switch is located, then it's quite easy to bypass it by just, the worst case, dremeling open the case, not touching that part of the... so this is an example of what that would look like. Bring up Google image search, find some, high resolution photos of the motherboard, and you can see quite clearly that that's the physical tamper switch. That's the SPI flash. They're on two different sides of the computer, so just don't touch that side of the computer. Open the other side of the case, and you'll be fine. BIOS security settings, they also depend on the integrity of the firmware and the firmware settings, the EFI variables we talked about. So they're not going to save you in this kind of scenario because they can be tampered with. So in summary, device encryption depends on the integrity of firmware and the firmware settings as well that we tampered in this example. So if you have a machine that's a bit older, then perhaps even tampering with the firmware code would be feasible. Like in the previous session, if you saw the EFI rootkit presentation. Physical attacks on firmware can, in almost every case, bypass all of the firmware security features. So that's something to be aware of. And so our summary of this is basically that existing mitigations in firmware and OS and firmware corporation aren't enough to protect you against these cold boot attacks, except for the one scenario that we showed where the machine is totally powered off and you have the pre-boot BitLocker PIN and TPM protections in place, which you might not be able to do if you're a small business or a consumer. If you're a corporation with an IT department that knows their stuff, then maybe they could configure that for you. But again, it's another password for users to remember and forget. And it is a bit of a hassle. We've heard feedback from different clients saying that it makes having a shared machine or a machine that's just lying there pre-configured to just give out to somebody who's forgot their machine or lost their machine, makes that a whole lot harder because you have to manually keep track of all these TPM or BitLocker passwords. So we had to put in a slide as well for the Microsoft people here or the developers in the audience. What can we kind of learn by generalizing from this and seeing what went wrong here, basically? So one thing would be, don't just adopt somebody else's threat model. When you import some piece of code, implement a specification. When you trust that somebody else has probably thought about these security things, just don't trust that implicitly. Actually have a look at what is your context, what's the context you're using the stuff in, what are the threats that are relevant to you and your users, and do your own threat modeling. Don't just rely on somebody else having done it before, because that's making assumptions about somebody else doing the work for you can be a problem.
And they also usually have a different mindset and thinking of a different kind of attacker. So we have heard a lot about nation-state attackers here, and most people will consider that out of scope. So
yeah, so not everybody might be interested in protecting against a physical attacker that's stolen a machine that specifically wants to steal your secrets from your machine. But if you do have that kind of an attacker in your threat model, if you really need to protect against that kind of attack, then yeah. So a vendor response slide as well, we have to put that in there. We've talked to Microsoft, we've talked to Intel, and basically the response is that the TCG specification or the TCG working group responsible for the specification has kind of decided that these kind of attacks are currently out of scope, and there's, not much they can do.
We should give them some credit because it was actually done in the same year as the attack was
And we should give Microsoft some credit as well. They've improved on the specification to actually make it harder to bypass this mitigation just using malware without physical access. And basically, as a operating system vendor, there's not much more Microsoft could do without the cooperation of the firmware people. So but that's the difficult part, and that's why this standard exists, is to make sure that the operating system people, the device manufacturers, the firmware people actually talk to each other and figure out how to solve this problem together. So going to client recommendations, people are actually using this and want to protect against this scenario. Keep firmware up to date. Firmware is software. It needs to be patched. Use those existing mitigations. Even though they're imperfect, they still put stumbling blocks in front of an attacker, might make it a bit harder for them. Worst case, it'll at least get rid of those people who don't have the the attack all planned out before. But another thing that's really important, don't just rely on full disk encryption. When you lose a device, don't just say, oh, it was encrypted, we're fine, not a problem. Actually have procedures in place to invalidate credentials. If there's VPN credentials on that machine, you want to invalidate those certificates, for example. Passwords need to be changed, all of that kind of stuff, to make it harder for to make the information that an attacker could steal off that machine as useless as possible to them, right? And be wary of those machines that might have been lost for a while and then suddenly magically reappeared. As I mentioned before, it's not just a confidentiality problem. We could just as easily have put a backdoor on there and then given the machine back to somebody. So basically conduct some kind of impact assessment to find out, is this kind of scenario relevant to us? Is it feasible to protect against, in our current situation? What would it cost to actually put those procedures and technical mitigations in place? And if justified by that impact assessment, you could, for example, use the pre-boot authentication and power policy to let Windows actually switch itself off after a certain amount of inactivity to make sure the machine is in a properly shut down state. Together with the TPM plus PIN pre-boot authentication, that is a safe state. You should also evaluate the effectiveness of these firmware protections we talked about. So, for example, the Intel boot guard, firmware signing, and other security features provided by the platform vendor, they may or may not be implemented correctly. You don't know, so you probably should go find out. And you could also consider adding like physical tamper-resistant measures, like just putting some epoxy over that chip, for example, making it a bit harder to connect to it. I mean, these machines that are in like a tablet form factor are usually harder to take apart. Not that that will prevent an attacker from performing this kind of attack, because they don't have to put it back together again. They just want the contents of the machine. But still, making it harder to get to that chip will still buy you time to, for example, respond and invalidate credentials or something like that. We have more content, but it's around other OSs and stuff, so we thought we'd rather just throw it open to questions at this point. And we'll see if questions about other OSs come up, then we might talk about that.
Hi, nice, very nice presentation. Thank you very much. Your video was about a very simple example to store password from, I think, Microsoft Word, but from your experience, did you achieve to recover, by example, a BitLocker volume key in memory?
Yeah. So that's what the demo was showing, is recovering the volume key for BitLocker out of RAM, using that volume key to mount the disk using Linux to be able to extract the secrets from the hard drive or potentially plant a backdoor. Okay. You could also steal other secrets from memory, like I mentioned, passwords or anything else that might be in memory. But once you have that's the juicy target, right? Stealing the volume keys, because then you have access to everything that was stored on the hard drive, all the secrets that were stored on the hard drive.
Okay, maybe the video was a shortcut, so we have not seen that. Thank you.
You said you mentioned you tried DMA attacks using Thunderbolt?
Yes.
Have you tried over a vacant PCI bus?
Yeah, actually, what we did in this case was on a PCI Express, not Thunderbolt. So since you're able to open the case, you have handy access to a PCI Express slot, that's prime target for DMA attacks as well. And that could also be performed either when the OS is booted up to steal volume keys or whatever from memory. It could also be used during the boot sequence when EFI is running to initialize the system to actually place a backdoor into the system at that point. So, yeah, good question.
A key part of this attack was the ability to disable the memory write feature.
Where are you?
Hey. Yeah. Being able to disable that memory wiping feature after the OS has crashed. Is there a reason that setting needs to exist in firmwares? Could they just always wipe memory if the OS has crashed?
They could. But they could wipe memory on every boot. Problem is that it takes a couple of seconds to wipe a couple of gigs of memory using just one processor core. So the platform vendors want to limit the boot time to the shortest amount possible, because that's it's a marketing requirement, user requirement. So that's competing with the security requirement. And the existence of this TCG platform reset mitigation spec is basically to weigh those against each other and find a scenario where you could, in the normal case, where the machine is going to be shut down properly, not have to do that, couple of seconds wiping procedure on every boot, but only when you actually detect that somebody has, or that the OS has crashed, and that's why we think the spec exists, is because the easy fix would be just to wipe memory on every boot and you'd be done with it. But since it takes time, people don't want to do that every time, and that's why we have these trade-offs.
Yeah, no, that implementation seems like a really good way of, as you said, not impacting performance on the standard boot scenario. So, but it would seem like the logical answer here for the firmware vendors would be, don't let people turn that off, because that way there would be no settings to overwrite.
It's hard. As it exists today, they'd have to integrity protect or just hide somewhere this variable instead of just leaving it open to anybody who can access the spy flash. Yep. So I mentioned there are some vendors who do a good job of trying to protect the password. Instead of having that just available as an NVRAM variable, they might, for example, hide it in the embedded controller that, back in the day used to control the keyboard on the laptop, that kind of thing, which makes it a bit harder to get to. Not impossible, but if you get EFI execution, then you could talk to that chip and so you can do things to kind of hide it and try to integrity protect it, but I think the real fix for this is probably to go back and have another look at the spec, see how can we retool this to actually work in a scenario where somebody has physical access to the machine. And that might mean, for example, using special area of memory, physical memory, to store secrets in that's always wiped. But it's a small area, so it doesn't impact performance. So that might be one, other trade-off that you can make. Mm-hmm.
So when you did the demo, was the machine right here?
Hey.
When you did the demo, was the machine powered off, or was it was it powered on or sleep?
Yeah, in the demo it was sleeping. Yeah,
it was sleeping. Okay. And were there, other than hibernate and power off, are there any other states where this attack is difficult?
not really, because if you have physical access to the machine, like I said, if it's off and you don't have pre-boot, you can just boot it up. Basically, the only state where it's hard is if it's hard to get the secrets loaded into memory in the first place, which is the scenario with TPM plus pin and powered off state. Nobody wants to know about other OSs? Okay, cool.
I was just about to ask that. Since you alluded to other operating systems, did you look at Macs with File Vault?
Yep, if that's what you want to see. So we'll just quickly go through this. So, for example, you don't want to leave your penguins showing either, so let's talk about that for a second. The Linux kernel actually received a patch from Matthew Garrett a year ago to implement this specification to set the more bit. Unfortunately, it's behind an if-def, so you actually have to know about it and enable it when you compile your kernel, and not all Linux distributions actually do that. So if you want to check for the support in your, hex dump that file in the sys file system and check the value there. If it's a 0, then the more bit is not set, which means that your Linux vendor should probably have a look at enabling that in the kernel. File Vault you mentioned, well, I think we have time to show you the demo on that as well. So let's do that. Or is it going to play?
It's moving.
It's moving, yeah. So this one's we can talk over it. It's a bit longer because it's not cut down like the one we showed you earlier, but it's basically showing you the same thing. So a user has secrets in a file on the hard drive. The attacker comes along, finds the machine in a booted up state, plugs in a USB drive. For convenience sake, the machine was already open. Cools down the RAM chips, and resets the machine with, I think it's Option Power. There you go. Boots it up again. Presses the Option key to get to the boot volume selection menu.
And you note in this case, there's no programming of the SPI flash actually.
So choose to boot from external USB drive, runs the tool to extract the secrets out of memory, reboots into Linux. That's just a Linux kernel booting. It's not very interesting, but soon we'll get a close-up of the screen where it actually shows you that the volume is mounted and the secrets off the hard drive have been stolen. So exactly the same scenario, exactly the same demo, but on a Touch Bar MacBook Pro. So we talked to Apple about that, of course. Their response was that in the very, very latest hardware models, so 2018 Touch Bar MacBook Pro and the latest Mac Pro? I'm not too sure about. You'll have to Google that. But those have a new chip called the Apple T2 chip, which is responsible for doing hard drive encryption. So they've moved full disk encryption functionality out of the operating system and onto a separate dedicated chip, which means that this attack scenario is no longer relevant to those machines. Also, they recommend setting a firmware password, which if a firmware password had been set on that machine, then Timo wouldn't have been able to just press the Option key to boot off of USB. He'd actually have to, get around the firmware password protection, which might be possible. Yep. Any other questions over there? We'll just put this slide up.
Hi.
Hey.
Right here.
Hey.
Very nice work, and I just have this sort of comment rather than question, which is you did say that, entering the PIN actually would stop. Configuring your BitLocker to require a PIN upon startup would actually prevent your attack. And I just opened my Windows machine here, and I look at BitLocker, and it says the recommended way to configure a BitLocker is to enter a PIN. So it looks like, so in some sense, it seems like from a security standpoint, making BitLocker not require entering a PIN is insecure, period. So they should, probably Microsoft should not even offer that option.
Yeah. So again, it's a usability thing, right?
Totally.
So not all the people that perhaps should or could enable the BitLocker PIN have done so because of usability issues. And what we want to spread awareness about is that those people might be at risk from this kind of attack. And we should give props to Microsoft as well for updating the documentation online to actually make it clearer the trade-offs involved. So that's good. Oh, we've got questions back there.
Given the RAM modules themselves these days have temperature diode on them, is that a way that they could use to mitigate the attack? Just detect a sudden drop and just wipe memory, or is there any way to attack even with that in case?
Yeah, that's probably too complex a scenario to actually be feasible in the real world. You also have to remember that all of these attacks that we're performing are done when the machine is in an off state, right? There's no power to the machine. Any kind of active measures like that would require some kind of thing to be, some kind of code or something to be active and actually clear memory contents before we get to resetting the machine and before we get to the power button.
You need a separate hardware solution for it. So.
Yeah, and still it would be a time race there, right? Yeah. So if we manage to cool down the RAM chips and then turn off the power so that, quickly enough that the active measure wouldn't have triggered yet, then, yeah, I don't think that's a viable option because it's a bit too complex and there's always going to be that race condition there.
Yeah. Have you done any testings with Optane as the memory instead of using RAM? The Intel new X points. We didn't mention that before, but there are several different other ways you could go about getting at contents of RAM. I mean, you could even, if you've got physical access and you have socketed RAM modules, for example, you could plug in like a DRAM emulator or something to get at the secrets in memory. So there are lots of different ways to actually do that, but it's all getting into the slightly theoretical at that point. We just want to show that today, this is a practical attack that anybody could carry out. And that probably needs some further work to make that harder again. Okay. So,
communicating with the RAM directly would be quite expensive compared to this, which is...
So we didn't mention, but the obvious solution to this is, of course, to implement some kind of RAM encryption in hardware, so that the memory controller would encrypt everything before going out to the RAM modules. But of course, that's totally feasible. That technology exists. It's just having some kind of high-speed encryption algorithm in hardware in the memory controller. But yeah, there's not much of a business case to be made there because it's just a security feature. It doesn't add anything else, and it's a lot of die space perhaps to devote to just that security feature. So that might be a possible way to fix it, but it comes at a cost.
Curiosity question, in your demos you're showing this cold boot being done with freeze spray. Is that enough to give you the time you need to dump?
Oh yeah, yeah. I mean, cooling the memory chips down to, I don't know, at least below freezing point, freezing point of water, gives you enough seconds to be able to perform this kind of attack. So we basically haven't hit that limit in our testing because, I mean, you only need like, what, at the most 5-10 seconds, and that's easily done by just cooling them down with some compressed air, or it's actually the driver gas, not the compressed air, but yeah.
Our colleague Timo actually managed to do this without cooling the RAM at all.
Yeah. Yeah. Depends on the normal running temperature of the machine and how if the RAM chips are being like pushed to their limit or not. So there's lots of variables in there. There's a lot of academic research in the past 10 years have gone into figuring out where these limits lie. So you can just go have a look at the academic papers on cold if you're interested in numbers around that. We don't have any numbers because, like I said, we haven't hit that limit in our testing. Thank you.
Hi, just to check. So basically, you were saying that once the machine is off, it's not exploitable for this case.
If you have pre-boot authentication with a BitLocker pin. Otherwise, you can just boot it up again.
Of course.
Yeah.
So during hibernation?
Yeah. So Hibernate will save the RAM contents to the encrypted volume and then shut down the machine properly. So hibernation is the same as power off, basically, when you're done with it. Yeah.
Okay.
Yeah.
And the last part is that those Intel SGX chips help?
Not really. I assume you're talking about the memory encryption stuff?
Yep.
Yeah, so like I said, the technology exists to do actual encryption of the RAM on the memory controller, and Intel has that kind of functionality bundled into the SGX stuff. As far as I know, it actually only protects the SGX enclaves and not all of memory, so I don't think it's a viable option to protect the BitLocker keys in that case.
Thank you.
But that technology could be extended to protect all of memory, right? But again, it's a trade-off because it requires some die space on the, I guess it's a PCH, the memory controller anyway. So, yeah.
Just a comment. I work for AMD. AMD does have on Ryzen processors total memory encryption. So we do have what we call a transparent system memory encryption that encrypts entire memory enabled through BIOS settings. So then it's the encryption engine is in the memory controller and it encrypts entire memory. So that's.
So does it then like randomize the key on each boot?
On each boot.
Yeah, yeah. So that's the kind of mitigation that we were talking about, where if you have something in the memory controller that would encrypt all of the RAM contents before they go out to the DRAM modules, and the key is randomized on every boot, then all of these attacks would be pretty much unfeasible. So that's pretty good mitigation.
Yeah, that's correct. That's available today.
Unless you can turn it off. If it's configurable, then yeah. Okay, so thank you very much.
Thanks.
Thank you, Ali and Pasi, for that great presentation.